Welcome. This is a two-lecture module on fault detection and classification, which everyone in a fab calls FDC. Here is a problem the module exists to solve. A tool finishes a process step. While it ran, it logged sensor traces, chamber pressure, RF power, gas flow, substrate temperature, a few thousand samples each. Before those wafers move to the next step, somebody has to decide whether that run was normal. Nobody measures the wafer at this point. The traces are all you have. Get it wrong in one direction and you ship a bad lot. Get it wrong in the other and you stop a tool that was working. Module has two lectures and the split between them is deliberate. In addition, we also have a supplementary lecture on the idea of principal component analysis, which we will use in both of these two lectures. Today, lecture 1 is about representation. Before you can say a run is abnormal, you need a description of what normal looks like, and that run turns out to be the hard part. We will build a population of healthy runs and you will see that no two of them are identical because the tool starts a few ticks early or late, the sensor gain drifts, 0 point moves. None of that is a fault. Then we will compress 2000 samples down to 3 numbers using principal component analysis, which we will explain in further details in the supplementary lecture. And we will look closely at those 3 numbers mean physically. Along the way, we will build 2 detectors any engineer reaches for first, watch both of them fail on runs we know are good, and work out why they failed and fix them with a single pre-processing step. Lecture 2 is about monitoring. It takes that model on a healthy run and runs it into a working detector. 2 statistics called t-squared and SPE, control limits measured from the baseline rather than chosen by hand, and an honest evaluation of runs the model never saw. It also asks the question a fab actually cares about, which is what such a system costs to run when the faults are rare, and it ends by placing the method next to autoencoders and deep learning, which is where the name of this course points. 2 practical notes. Everything in both lectures uses a synthetic data set, 100 healthy runs to build on, 40 more held back and 48 faulty ones across 6 fault types. It is synthetic because that way we know the ground truth exists and we can turn the faults up and down and watch what happens. Each lecture has a companion notebook that reproduces every figure from scratch in NumPy and Matplotlib with nothing hidden in a library. If a number on a slide surprises you, you can change a constant in the notebook and find out why. We start with why anybody uses the trace at all. A fab measures wafers with metrology and metrology is accurate. It is also slow and it is sampled. You measure a few wafers per lot and the results come back hours or days later. If the chamber started drifting this morning, metrology tells you about it on Thursday and by then you have run several thousand more wafers through it. Meanwhile, the tool is already recording. Every process step logs its sensors and typically somewhere between 1 and 10 samples per second. That record exists for every single run. It exists immediately and it costs nothing extra because the sensors are already installed and already logging. So the idea behind FDC is to use that record as an early indicator. The chain on the left is the standard one. The equipment publishes sensor data. A historian stores it with the context you need to interpret it later, which lot, which wafer, which chamber, which recipe. An FDC engine scores every completed run against a model of what the normal looks like. If the score is out of limits, an out of control action plan routes it to a human which decide whether to stop the tool. 1 point on vocabulary before we go on. Detection answers whether the run is abnormal. Classification answer what kind of abnormal it is. Today's detection, classification comes next lecture. Before we pick a signal to work on, look at what these traces actually look like across different processes. Top left is atomic layer deposition. The recipe is a pulse train, so the trace is periodic, 1 cycle per dose. Top right is a plasma etch. Power ramps up, holds, and the step ends when the optical emission signal says the film has cleared. That end point is why etch steps do not all have the same duration. Bottom left is a rapid thermal anneal. Temperature spikes, holds briefly, and comes back. Bottom right is CVD or PCVD. Pressure rises to a set point, holds for the deposition, and comes back down. One plateau. 4 different processes, 4 different shapes, What they have in common is listed on the right. Each one is a bounded step with a known start and end. Each one repeats thousands of times a week. Each one has a control loop driving the signal to a target and holding it there. And each one shows run-to-run variation even when the tool is perfectly healthy. That last point is the one that will occupy most of today. One more thing about real setting before we simplify it. A single H or CVD step does not log one sensor. It logs dozens. This figure shows 4 of them from the same step: RF power, pressure, gas flow, chamber wall temperature. They all move together because they are all following the same recipe envelope. That means they are heavily correlated, and a method treats them as independent is throwing that information away. It also means some faults live in the relationship between the channels rather than a single one. Pressure can be in the range and flow can be in the range while their ratio is wrong. So you would never see that by monitoring either channel alone. We are going to model one channel today. I want to be clear that this makes the problem easier, not harder. Everything we find will be still there when we add channels, and some of it gets worse. The numbers at the bottom are operating envelope you are working inside. Hundreds of process steps per wafer, 1 to 10 samples per second per channel. About 1% of runs genuinely fall, and the scoring has to finish between wafers, which is a few seconds, so whatever we build has to be cheap and fast. This is the signal we will use for the rest of the lecture. It is the CVD single plateau shape from 2 slides ago, sampled at 2000 points. Think of the vertical axis as pressure in millitorr if that helps. The unit does not matter for anything we do. 5 phases, and it is worth naming them because we will refer to them all hour. Idle, sitting at the baseline of 20. Ramp up, where the controller drives the signal to the set point. Overshoot and settle, where the loop slightly overshoots and then damps out. The plateau holding at 250 with a small ripple and a slow downward drift, and then ramp down back to baseline. 2 things to fix in your head. First, the overshoot, the ripple, and the drift are normal. They are what a real control loop does. A trace that jumps instantly to state point and sat flatly would be a strange one. Second, this deterministic shape has a name we will use constantly: the golden trace. Every detector we build today compares a run against that golden trace. Here is the problem in the form we will actually solve it. You are given a set of traces from runs that are known to be good. One channel, one recipe step, all same length. From those you build a model of what normal looks like. And then a new run arrives and you produce one number, and you will compare the number against a limit. Notice what is absent from the diagram. There are no faulty runs in it anywhere. You do not have examples of what wrong looks like, and you can not ask for them. Three reasons. Faults are rare, around 1% of runs. And when they do happen, you find out late because the evidence is a metrology result that arrives days later. And the list of possible faults is open-ended because a tool that has been running for 2 years finds new ways to fail. This setup has a name. It is called one-class monitoring, and it is the actual industrial problem rather than a simplification we are making for the teaching. You learn what normal looks like, and anything that does not fit gets flagged. Before we start building, I want you to see why this is worth any effort at all. On the left is a healthy run, in the middle a run with a fault. Look at them at this scale and they're the same picture. Same ramp, same overshoot, same plateau, same duration. The right panel magnifies the plateau with the 100 healthy runs in gray behind and their mean in teal. The faulty run sits about 11 units below the whole healthy population for the entire hold. What happened physically is a miscalibrated set point. The controller did its job perfectly. It held the pressure tight and stable at the wrong value. Every wafer in that run is out of spec. The number underneath gives you the scale. The injected offset is 10.4 units, which is 4.5% of the 230 unit span. The healthy plateau varies by about 2.4 units, one standard deviation across the 100 runs. So the fault is roughly 4 times the normal plateau spread, clearly outside the normal variation and completely invisible to eye at the full scale. Hold on to that number 10 units. We will come back to it repeatedly. A short slide where the data comes from, because you should know what you are looking at. Everything in these two lectures is generated rather than logged from a real tool. The generator is on the left. This is one deterministic function that produces the golden trace and 5 knobs that get a fresh random value for each run. A time shift, a gain and offset, measurement noise and jitter on the ripple and drift. Fix it so every number on this slide regenerates exactly, and the lab notebook produces all of them. Two separate sets of runs described on the right. It is worth keeping them straight. The first is 100 healthy runs. A health gate rejects any run whose idle level, plateau or overshoot straight too far. So all 100 runs are good by construction. Every measurement in this lecture comes from those 100. The second set is 188 label runs generated from the same model with one defect injected into 48 of them. Those supply the faulty traces you will see in the next few slides, and they become the scoring set for next lecture. The faulty run on the previous slide came from that second set. There is no faulty run anywhere in the 100. Here is the dataset written out as a table because it helps to see the shape of what we are working with. One row per run. The trace column is the actual signal, 2000 samples. Then the values of the knob that reproduce it, the time shift in ticks, gain, offset, ripple amplitude and the drift. X is 100 by 2000 arrays of floating point numbers. The rows are runs, columns at time points. 200,000 numbers in total, which is nothing by modern standards and fits comfortably in memory. The important line is in the card on the left. The detector sees the trace column, 2000 numbers per run and nothing else. Those knob columns exist here only because we generated the data ourselves, and we are going to use them later as an answer key to check what the method found. In a fab, you do not have them. This is the healthy population. The same recipe step, run 100 times. 10 of them are shown here so you can see the individual traces as readable size. 3 things to notice. The shape repeats every single time. The ramp timing shifts a little from run to run, and the plateau level and the ripple move a little as well. None of that is a defect. All 100 runs pass the hell gate. This is what healthy variations look like, and the detector has to tolerate every bit of it without complaining. 100 runs is a realistic size for a production baseline. Next lecture, we measure what happens when you try to do this with far fewer. Since we generated the data, we can look at the knobs directly. Every histogram holds 100 values, 1 per run. Solid line is the mean. Dashed line are the 1 standard deviation either side. Time shift standard deviation of 6 ticks. The generator clips it at plus minus 15, which is why we observe start time span 280 to 310. Gain about 1% scaling. Offset a little under 1 unit. Ripple amplitude and plateau drift both small. Two things worth pointing out. The measured standard deviation land close to the values where they were drawn from, which is what 100 sample buys you. If you had 20 runs instead, these estimates would be off by 20 to 30%, and some of the analysis later would be much less clean. The second point is that the measurement noise does not appear here because it is drawn per sample rather than per run. It is white noise of about half a unit plus a slower wander of about a third of a unit. Now the slide that sets up the whole rest of the lecture. The previous slide showed the knob in their own units, ticks, percent or units of signal. Those are not comparable to each other. This slide converts all of them to the same currency, which is the sensor units of the trace. All 100 runs are overlaid. Each phase of the step is boxed, and underneath each box you have the parameter that dominates the spread there and the size of that spread. Start at the idle section, box 1 and 6. 1.3 units. That is the offset knot and the measurement noise, and it is small. The plateau, box 4, 2.8 units. Gain, ripple and drift together. Overshoot and settle, box 3, 4.3 units. A bit larger because the gain and overshoot jitter both act there. Now the two ramps, 24 units and 17 units. 10 times between everything else, 10 times everything else, and all of it comes from the time shift. Here is the arithmetic behind it. The standard deviation of the start time is 6 ticks. 6 ticks out of 2000 is 3% of 1% of the run. The 6 ticks out of 2000 is 3/10 of 1% of the run. On the plateau, where the signal is flat, the shifting a run by 6 ticks changes almost nothing. On the ramp, the signal is climbing at about 4 units per tick. So 6 ticks of shift moves the value at any given point by roughly 24 units. Compare that with the set point fault from slide 7, which moved the plateau by 10 units. The largest source of variation among healthy runs is more than twice the size of the fault we are trying to catch, and it has nothing to do with the wafer quality. Before we start modeling, here is what actually wrong looks like. 6 fault types, each with the physical cause underneath and the phase it lives in. Slow ramp, a sticky value or a weak drive, so the signal takes longer to reach the set point. Leaves on the rising edge, set point offset, a miscalibration. That plateau holds at a wrong level. That is the one from slide 7. Plateau droop, a failing heater or a slow leak, so the level sags over the hold. Excess overshoot, the control loop tuning gone soft, so it rings longer. Glitch spike, an arc and ESD event, a brief disturbance. Noise burst, control instability or a loose connector, so a stretch of the plateau becomes abnormally noisy. The gray band beside each panel is the same 100 healthy runs, so you can see how far outside the normal fault sits. These traces are here, so the failure modes are concrete in your head. Nothing we measure today is computing from them. Everything today uses healthy runs only. Now we start building the representation. Here is the move that makes everything else possible. Take a trace, read the values off in order, write them as one long list, 2000 numbers. That is the vector, and the run is a single point in the 2000 dimensional space. If that sounds abstract, the comparisons to images help. If this is all new to you, I recommend you watch the accompanying lecture on image recognition using principal component analysis. A 128 by 128 grayscale photograph is 16,384 numbers written out in a row, and every method for face recognition starts by doing exactly this. Stack all 100 runs and get a matrix, 100 rows by 2000 columns. Rows are runs, columns are time points. Everything for the rest of these 2 lectures operate on that matrix. If this is not familiar to you, I recommend you watch the accompanying video on facial recognition based on the PCA analysis. Step 1. Average the 100 vectors element by element. The result is a trace, and it looks like what all the runs have in common. It sits close to the deterministic golden shape. The distance between the mean run and the golden trace is about 46 units against 165 of a typical individual run. So the mean captures the part that every run shares. Once we subtract it, what remains for each run is the only part where the run drifts from the others. That is the part we want to study. Step 2. Subtract the mean from every run. The row on the top shows 3 raw runs. The bottom row shows the same 3 after subtraction. Those bottom curves are the deviation, and they are what PCA will actually be given. The mean run gets scored once and added back at the end. Look at where the deviations are large. 2 big wiggles both sitting on the ramps. Almost nothing on the plateau or at idle. This is the same fact from slide 12, seen as a difference. The timing shift moves the signal a long way where the signal is changing fast, and almost not at all where it is flat. Step 3. We now have 100 deviation curves, and we want to know what patterns they share. Principal component analysis answers that. Formally, it finds that the directions along which the data varies most, ordered by how much variance each accounts for. Informally, and more usefully here, it hands back a set of trace shape patterns that every deviation curve can be written as a composition of them. Those patterns are what you see on the slide because they came from a principal component analysis, and because they are shaped like traces, we call them eigentraces. The name comes from eigenfaces, which is the same construction principle of photographs of faces. The mathematics is identical, only the inputs changed. Look at the percentages. The first pattern accounts for 82% of all variation between runs. The second 13, the third 1.5. After that, it drops off quickly. So a 100 run varies in 2000 dimension turns out to vary mostly along two directions. We do not yet know what those directions mean physically. That comes in a few slides. Step 4 is the part that makes this useful. Any run can be written as the mean run plus a certain amount of the first eigentrace plus a certain amount of second and so on. The figure shows it literally. Mean run minus 316 times E1 minus 39 times E2 minus 8 times E3, and the rebuilt run on the right sits on top of the real one. The code underneath is the entire method in 5 lines. Compute the mean, take the singular value decomposition of the central data, keep the first k rows, which are your eigen traces, project each run onto them to get k numbers, multiply back to rebuild them. 2 lines to notice. The projection line turns 200 numbers into k numbers. The reconstruction line returns them back. Everything else in these two results is built on those two operations. The coefficient spreads on the right tell you the relative importance. E1 coefficient range over roughly plus minus 218 units, E2 over 88, and E6, and by E6 you are down to 10. Here is the same idea shown in 3 individual runs. The set of eigentraces is fixed. It is the same set for every run in the data set. What distinguishes one run from another is the list of coefficients on the right. Run 2 has a small first coefficient, minus 12, and its largest is the second one at plus 49. Run 10 has minus 193 on the first. Run 18 has minus 221 on the first and the minus 107 on the second. Look at how quickly the bars die out. By the fifth component, they are barely visible. The annotation on the row makes that precise. Rebuilding each of these runs from the first 4 coefficient alone gets you to within 0.3% of the signal span. So a run that arrives at 2000 numbers can be described by 4 with an error you would struggle to see on the plot. Now we work out what these patterns actually mean physically. The method is very simple. Take the mean run, add a multiple of one eigentrace on it, and watch what part of the trace moves. Each row does that for one component, zoomed on the region where the movement happens. The black curve is the mean run, and the colored curves are the mean plus minus 1 or 2 standard deviation of that component. Turn E1 and the whole line slides either earlier or later in time. The shape is untouched. Turn E2, the plateau rises and falls, the timing is untouched. Turn E4, the whole floor lifts and drops and nothing else moves. E3, E5, E6 produce small changes with no single obvious target, so I left them alone. The slide is observation only. Watching something move is suggestive, but it is not proof. Next slide gives the evidence. 2 independent checks on each component. The top row asks where the pattern puts its energy. If a pattern is essentially 0 everywhere except 2 ramps, it cannot be describing the plateau level, whatever else it might be doing. E1 has 96% of its energy in 2 edges and 1% on the plateau. E2 has 92% on the plateau. E4 has 84% in flat regions at either end. The bottom row asks a completely separate question. For each run, take that component coefficients and plot it against a quantity measured on the straight of the raw trace. No generator knobs are used here. These are all things you could measure from log data. E1 against tick, where the run crosses 50% of its span, which is a direct measurement of when the run started, correlation of 1.00, a straight line. E2 against the measured plateau level, 0.998. E4 against the measured idle level, 0.88. Two independent lines of evidence pointing the same way in each case, where the energy sits and what the coefficient tracks. That is enough to name them. E1 is the clock, E2 is the sensor gain, and E4 is the sensor offset. Let me do the accounting exhaustively rather than for 3 hand-picked components, because the exhaustive version is more informative. Down the side, every parameter in the generator draws fresh from each run. Along the top, first 8 components with their variance shares. Each cell is the absolute correlation between that parameter and that coefficient. Right hand panel is the control. With 100 runs, if you correlate a random quantity against 8 components and keep the best ones, you get around 0.17 by chance, and the 95th percentile is 0.27. So anything below that 0.3 is not evidence of anything. Box cells are the ones that clear it. 4 parameters clear it. Time shift on E1 at 1.00, gain on E2 at 0.92, offset on E2 on 0.86, and plateau drift on E8 at 0.35, which is weak but real. 5 do not. The overshoot, ripple amplitude, ripple period, ripple phase, and the measurement noise, nothing they touch gets above 0.16. There is a reason for the shift, and it is structural. PCA find direction. A parameter becomes a single component when its effect is one fixed shape multiplied by a number. If time shift is to first order, gain is, the additive offset is. Ripple phase is not, because shifting a phase rotates the waveform rather than scaling it, and PCA needs at least 2 components to represent it. Noise has no fixed shape at all. One more thing to notice, on E3 column, E3 carries 1.5% of variance more than E4. It matches nothing. So the ordering by variance and ordering by interpretability are the same things. Same information collapsed to the single strongest correlation each parameter reaches. This is the version to remember. 4 parameters above the chance line, time shift, gain offset, and weekly plateau drift. 5 below it. I want to draw your attention to the top bar specifically. The first component carries 82% of all variation in the dataset, and what it is reporting is when each run starts. The start time is a real property of each run. It is measurable. It varies by plus minus 15 ticks, and it has no bearing on whatsoever on whether the wafer came out in spec. So the dominant structure that our model has learned is a property that we don't care about. Keep that in mind for the next few slides. One practical question before we move on. How many of these numbers do you actually need? The panels rebuilt a run from the increasing number of components with the average error under 1% of the signal span. 0 components, which is just the mean, gives you 1.4%. 3 components, 0.3%. Beyond 5, it stops improving. The last 2 panels are a different set. Feed models something that is not processed rate at all, a square shape, pure noise, square pulse comes back 7% error. Pure noise, 23% error. 20 to 70 times worse than a real run. Now we build the detector. Here is the first thing anyone writes. Subtract the golden trace from each run. Take the largest absolute gap everywhere in the run. If it exceeds a threshold, flag the run. 2 lines of code, and this is perfectly sensible to try. The threshold here is 20 units. So now run it on 100 healthy runs, which we know are all good. 38 of the 100 runs exceeded. Every one of those 38 passed the healthy gate. The detector is calling more than a third of known good populations bad. Look at where the residuals live in the plot on the left. 2 enormous lobes, one on each ramp, reaching 60 units. On the plateau, it stays inside 10. And here is the bind that puts you in. To stop the ramps from tripping, the threshold has to be at least 20. But the set point fault from slide 7 only moves the plateau by 10 units. A threshold loose enough to survive the healthy ramp is too loose to catch the fault. Second attempt. Drop the handbill reference entirely and let the data speak. Run PCA on the 100 runs. Keep the first two components. Plot each run as a point in that plane and look at the outliers. One line of code. This is the standard unsupervised approach to anomaly detection, and it is a reasonable thing to reach for. Here is what comes back. The first component carries 82% of the variance. The scatter on the right is colored by when each run started, and the colors run cleanly from one side to the other. The correlation between the first component score and the start time is 0.9997. The spread across that line is plus or minus 280 units, which is large. The run sitting at the two extremes are simply the earliest and the latest starter, and all 100 of them are healthy. Notice what changed between here and the interlude. Earlier we asked PCA to describe the 100 runs and it did that well. Here we are asking it to rank them, which is a different question with the same arithmetic. Both detectors are behaving badly and they have the same cause. The figure shows the first eigenstate in red learned from 100 runs and the derivative of the golden trace as the dashed line. The PCA was never shown the golden trace. It recovered its derivative from the data with a cosine similarity of 0.995. Once you know that, both failures follow. Take the residual detector first. The residue is the run minus the golden trace. If a run is shifted by a time delta, then at each point that difference is approximately delta times the local slope. On the plateau, the slope is about 0, so a few ticks of shift costs nothing. On the ramp, the slope reaches about 4 units per tick, so 6 ticks of shift produces roughly 24 units of residual. The two lobes are that identity and they sit exactly on the two ramps because this is where the slope is large. Now PCA. There is a first order approximation you have all seen. Y of t plus delta is approximately y of t plus delta times y prime of t. Read that as a statement about the data set. 100 runs with random shifts spread out along the direction y prime of t. The amount of spread is proportional to the size of the shift. Since the shifts are the largest source of variation in the data, that direction becomes the first principal component. So one cause, two symptoms. Both detectors are measuring the clock. The start time is measurable. It varies by plus minus 15 ticks and it has no bearing on wafer quality. A parameter like that has a name, a nuisance parameter. Real but uninformative about the question you are asking. 3 things you could do about it. First, raise the threshold. Loosen it until the ramps stop tripping, which takes you from 20 units to 45 or more. Now, nothing on the plateau under 45 units get caught and the 10 unit set point fault sails through. You have bought silence by giving up detection across the entire plateau. Second, mask the ramps. Score the plateau only and ignore the transitions. The ramp stop contributing residual, which solves the immediate problem. But a slow ramp fault and an excessive overshoot both live in the region you just deleted. So those become undetectable. Third, align each run first. Estimate the shift for that run and undo it and then score. One number per run, no training set, no fitted parameters, no threshold to tune. Third option is the one to take, and the reason is that it removes the nuisance parameter instead of hiding it. The ramp stays available for detection and the plateau threshold stays straight. There is a general lesson here and that outlives this example. When an unsupervised method finds something enormous and unhelpful, look at the representation you handed it before you go shopping for a bigger model. Alignment on batch trajectory is a well-developed topic. 4 approaches in rough order of how much freedom they give themselves. Landmark alignment. Find a repeatable event in each run, such as the tick where the signal first crosses half of its span, and shift the run so that the event lands at a fixed index. 1 parameter per run. This is what we'll use. Cross correlation. Slide each run against the reference and take the lag with the highest correlation. Also 1 parameter per run, and it handles pure translations well. Dynamic time warping. Find a monotone mapping between the run's time axis and the references so the run can stretch as well as shift. Many parameters, powerful and with a warning attached. Given enough freedom, it can bend genuinely a faulty run back into a healthy shape and hide the fault. Resampling to a fixed length using the recipe step boundaries to normalize each phase. This needs a step boundary which comes from context data rather than from the trace itself. 2 cautions worth carrying with you. First, if a fault itself is a timing fault, alignment can absorb it. A slow ramp survives because it changes the slope and not just the crossing point. But a run that simply started late would be erased. Second, a landmark has to exist. A run that never reaches a set point has no 50% crossing, and your code needs a defined path for that. Landmark alignment in detail because it is 3 lines and worth saying. Take the run, compute the midpoint between its maximum and minimum. Find the first tick where the run crosses that midpoint on the way up. That is the landmark. Shift the run so the landmark lands on a fixed reference index. The left panel shows the raw runs at the rising edge and each crossing the midpoint at its own tick. The right panel shows them after the shift, all crossing at the same place. What this costs is 1 integer per run computed from the run itself. There is no training set, no fitted parameters, no threshold. Compare that against the alternative from 2 slides ago, both of which required a human to decide what to loosen and where to mask. Now rerun the first detector on the aligned data. Same rule, same threshold, different inputs. Before, 38 of 100 healthy run exceeded plus minus 20, now 0. The mean peak residual drops from 20 units to 5. The largest residual anywhere in the data drops from 60 units to 10. That last number is the one that matters operationally. With the ramps quiet, the threshold can come down from 20 units to about 8, which is now below 10 units set point fault. The detector can catch the fault from slide 7, which it could not do before. Nothing about the detector changed, 1 pre-processing step on the input. Same for the second detector. Same PCA applied to the aligned runs. The correlation between the first component and the start time falls from 0.997 to 0.026. The total variance across the 100 runs falls from 57,900 to 9,500, which is a reduction of 84%. The spread across the first component goes from plus minus 218 to plus minus 88. Now here is the line I want you to be careful with. The variance share of the first component reads 82% before and 82.5% after. If you reported only that ratio, you could conclude that nothing happened. The reason the ratio does not move is that the numerator and denominator both collapse together. 84% of absolute variance in this data set disappeared, and the ratio cannot show you that. The last row of the card makes the mechanism explicit. The first 2 components is the old second component and essentially untouched. Cosine similarity 0.998, and its absolute variance barely changes from 7,750 to 7,830. Alignment does not shrink the gain mode. It removes the mode that had been sitting on top of it, and everything below moves up 1 place. When you report on the pre-processing step, report the absolute variance. Here the eigentraces themselves before and after side by side. Top row before. The first component is the pair of spikes sitting on the 2 ramps. The third component is the same thing again, a sharper pair of spikes on the same 2 ramps carrying 1.5%. So the 2 of the 4 components are describing timing. The second is the plateau block, and the fourth is the idle level. Bottom row after. Nothing edge localized survives at all. The first component is the clean plateau block tracking the plateau level with a correlation of 1.00. The second is the idle level at 0.90. The third and fourth are oscillatory patterns on the plateau that match no single parameter. That first panel is the whole story of this lecture in one picture. It goes from a pair of spikes at the ramps to a flat block on the plateau. Both the leading component described when the run started. After, it described the plateau level, which is the set point, which is a quantity a process engineer actually monitors. Same comparison done with the correlation evidence rather than the waveforms. Three quantities across the columns, each measured directly on the raw traces. Start time, plateau level, idle level. Top row is before alignment, bottom row is after. In every panel, I searched all the components and plotted the one that tracks the quantity most closely. So the component index in each title is a result rather than a choice. The panel to look at is the bottom left, start time after alignment. The best any component manages is 0.09 and the scatter has no structure at all. It is the only shapeless cloud in the figure. That is what removing a nuisance parameter looks like, stated as a negative result. The same three runs from earlier, now decomposed both ways on a shared vertical scale. The left column zooms the rising edge so you can see the correction, gray before and navy after. Runs 10 and 18 had first coefficients of minus 193 and minus 221 purely because they started early and late. After alignment, their coefficient leads shortened by more than half from 214 to 91, from 247 to 114. The run 2 is the control. It started close to average, so there was no timing error in it to remove. Its least length barely moves from 54 to 57. That is the check that alignment is removing one specific thing rather than shrinking everything. And the meaning of the first coefficient changes underneath. Run 18 goes from minus 221 to plus 110. Before that, the number meant the run started late. After that, it means the plateau sits high. Same position on the list, different physical quantity. Finally, the full accounting before and after. Every parameter the generator draws search against the first 8 components in both conditions with the chance level marked to 0.27. The time shift goes from 1.00 on the first component to 0.09 on any of them. It has left the model entirely. The gain holds a 0.92 and moves from the second component to the first. Offset holds around 0.9 and moves from the fourth to the second. Plateau drift holds from 0.36 and stays on the 8. The 5 parameters that were below chance before is still below chance after. So the statement about alignment can be made precisely. It removes one parameter from the model and it promotes everything that was below it. No parameter that was invisible before becomes visible. No parameter that was visible is lost. That is a narrower claim, and it is the kind of claim you should want before you put a pre-processing step into a production pipeline. 4 things to take away, all of them measured on 100 healthy runs with no label faults anywhere. First, a fault can hold a completely correct shape at the wrong level. The set point offset moves the plateau by 10 units on a 230 unit span, about 4 times the healthy plateau spread, and that stayed inside normal variation everywhere else. Anything obvious enough to see by eye was usually already tripped the limit somewhere. Second, you define normal from good runs because good runs are what you have. Faults are rare and they are discovered late, and the catalog is open-minded. 1+ monitoring is a real problem rather than a teaching simplification. Third, 2000 samples per run to reduce about 4 numbers. The mean plus 3 or 4 eigenstate reproduce a healthy run to 0.3% of its span, and the leftover error separates real run from the shapes the model has no ingredients for. That leftover becomes half of the next lecture's detector. Fourth, both detectors measured the start time. Neither was implemented wrongly. They reported a large source of variation in the data, and the largest source was a nuisance parameter. One alignment pass took the peak residual from 20 units to 5, and the correlation between the first component and the start time from 0.997 to 0.0 to 6. Next lecture we set a threshold with an actual justification. Instead of picking 20 by hand, we bring in label false for the first time and we find out whether either of these detectors is any good.